So today we are going to learn about momentum and also about the principle of conservation of momentum. So let's begin with momentum. Every moving object has a momentum. Momentum is a measure of how hard it is to stop something that is moving. An object that is moving that has a higher mass and is moving at a velocity v, and an object that has a lower mass and is moving at the same velocity v. If we compare the momentum between the two objects, then the objects with a higher mass would have a higher momentum. Also, if an object when it's moved at a velocity v and when it's moved at a much greater velocity, that is greater than v, the momentum would also be higher. So when an object has a greater mass and has greater velocity, the momentum is higher. That means an object that has greater momentum would be hard to stop. So without any mathematical definition, we can define momentum as a measure that defines how hard it is to stop something that is moving. Mathematically, we can write momentum equals to mass into velocity. Momentum of an object is its mass and the multiplication of the mass with the velocity. So when an object is not moving, it does not have any momentum. The momentum is 0. Because the velocity is 0, that means multiplying anything with 0 makes 0, so momentum is 0. Another thing is that momentum is a vector quantity, because velocity here in this equation p equals to mv, velocity is a vector quantity. So momentum is x in the direction of the velocity. If momentum is in this direction, then the object is moving in this direction. That's how momentum is related to velocity, and it's a vector quantity. So that means as mass has unit of kg and velocity has unit of meter per second, that means unit of momentum is kg meter per second. Now let's relate force with momentum. When an unbalanced force, that means a resultant force, acts on an object, there is a change in momentum. There is a change in momentum in the direction of the resultant force. So here I am showing that a car is moving at velocity u. It's the initial velocity. Let's say after time t, let's say force is applied. Then the initial velocity was u, then force is applied in this direction. That means from earlier lectures we can sense that the car would now accelerate, because now there is a resultant force acting on the car. This is the resultant force. Let's say there is a resultant force of F is acting on the car. So what happens is that the car velocity would change after increasing the applying the resultant force for a time t, for time of t second, the car's velocity changes, it increases in the direction of the force. So we can sense that the momentum increases from mu, that is the initial momentum, it increases from mu to mv. The momentum is changing. So what we can write is that as force is the rate of change of momentum, we can say that force equals to final momentum. As the, let's say the mass of the object is m, the final velocity of the car after applying the resultant force F for time t is v. So final momentum is mv minus mass into initial momentum, mass into initial velocity, that is the initial momentum. Initial velocity is the velocity before the resultant force is applied on the object. It's a change of momentum divided by time. Force is change of momentum divided by time, and that means rate of change of momentum. From this equation, we can also derive the force equals to mass into acceleration. Let's see how we can do this. If we take m common, the mass common, we get m into v minus u by t. Let's write m into v minus u by t, v minus u by t, and this part change of velocity, rate of change of velocity is acceleration. That is how we can derive force equals to mass into acceleration from force equals to rate of change of momentum. And this thing here we have written, we can say also say force equals to change of momentum, change of, let's write p, as we denote momentum by p usually in physics, divided by t. If we take t from right hand side to the left hand side, we get F into t equals to del p, that is change of momentum. And this quantity here, F into t, is the impulse. Impulse is a measure. From the equation we can already guess that impulse is a measure of change of momentum. When a force acts for a time t and the momentum change that occurs is the impulse, and as force has a unit of Newton and time has SI unit of second, so the unit of impulse is Newton second. This is the unit of impulse. Okay. Now we will move on to collisions. We have already learned that impulse of a force acting on an object for time t is the change of momentum. So here we can see a scenario where there are two balls A and B. These are two objects. A is an object, B is another object. A has a mass of m and B has a mass of m1. And this scenario is just before collision. This is during the collision, this is during the collision, and this is after the collision. So let's look here. So here we can see that the object B with mass m1 is at rest, and the object A of mass is moving, mass m is moving towards B with a velocity of u meter per second. This is just before collision, and during collision during the impact, during collision, when A and B touches one another, A is exerting a force, let us say F, force of size F on B. A is exerting force of size F on B. At the same time, B is also exerting the same force on A, and this is related to the Newton's third law of motion. Newton's third law. Newton's third law of motion. B was not moving initially, but it is also exerting a force F on A. This is due to Newton's third law of motion, which states that for every action there is a reaction force. So, when object A exerts a force of F on B, B is also exerting the same amount of force on A, and this is during their point of contact, during the collision, and let us say they are in contact for time t. Let us say they are in contact for time t. As we have already seen that force into time gives us impulse, force into time is the impulse. So, as force F is now acting on B for time t, the object B will now experience a change in momentum. So, initially it was not moving, it was at rest, that means its velocity was 0. Now it will start to move due to force F acting on it. So, the momentum of object B will change, it will now increase in the direction of force. So, we have seen that we have already said that the force acting on A and the force acting on B is the same, and they are in contact for the same time. So, A and B both are experiencing the equal change in momentum. That means the momentum B will gain momentum of F into t. At the same time, A will lose momentum of F into t. That means momentum of A will decrease by F into t, and momentum of B will increase by F into t. That is the change of the momentum. The momentum that means the momentum that is lost by A is gained by the object B. Just after collision, the object B with mass m1 is now moving with velocity v2, and the object A with mass m is moving with velocity v1. From here, we can rearrange the equation in here. Okay, one thing I should mention is that, as we have seen that momentum that is decreased for A is gained by B. From here we can say that momentum is conserved. The total momentum is conserved before and after collision. That means momentum before collision equals to momentum after collision. So, we can write momentum before collision from this situation here. The object A has mass m into u. It was initially moving with velocity u, and the object B had have a mass of m1, but it was at rest, so its velocity is 0. equals to momentum after collision. That means this scenario here, for object A the momentum is m into v1. For object B its momentum is now m2 into v2, sorry, m1 into v2, as mass of object B was m1. So we can write mu equals to mv1 plus m1 v2. So in exams, if there were situations where the velocity of this object is given, mass of both of the object is given, and velocity of one of the object was given, in that situation we could use the equation to find the velocity of the other object. But here we should take into account the direction. There could have been there could be some situations where if the objects have almost same mass, there could be situations that the this object would move in the other direction. So when taking this into account, if this direction is positive, if I take this direction is positive, and if the object moves in the other direction, we should take the velocity as negative. That's what we should be careful about during exam. So that's all about momentum, law of conservation of momentum.